And in practice, this is considered a solved problem in the sense that there's software that almost always works. Okay, most of us have probably not encountered a matrix where MATLAB fails to compute the eigenvalues. Nonetheless, such matrices do exist. So every few years, like somebody finds a matrix where this LAPACK or MATLAB or the software that we use doesn't work. And the reason is that the software is actually based on heuristics that are not provable algorithms. So the goal of this talk is not to improve the actual software that people use, but to produce algorithms that are provably always correct, so we can avoid this situation of having to occasionally fail. So this is a theoretical question about theoretical analysis of algorithms. And the second distinction, which is important, is that there's a big distinction in this problem between normal matrices and non-normal matrices. Okay, so normal matrix is a matrix that commutes with its adjoint. So a special case is a Hermitian matrix. And for normal matrices, it has been known for, I don't know, I guess 50 plus years that actually there are good provable algorithms for this problem. So if the matrix is normal, there's a famous result of Wilkinson from 1968 with refinement by Decker and Traub, who showed that if the matrix is normal, then indeed you can solve this problem using n cubed log n over epsilon operations with log n over epsilon bits of precision. Okay, and this roughly matches what we see in practice. So for normal matrices, theory and practice are close to each other. The real challenge is we don't know results like this for general matrices. Okay, and so throughout the talk, this is kind of going to be the benchmark we're going to compare ourselves to. We would like results for general matrices that are as good as the provable results for normal matrices. And why is there such a big distinction between normal and non-normal matrices? Well, really, I mean, if I had to give you one reason, it's that non-normal matrices can have highly unstable eigenvalues. Okay, so if you have a non-normal matrix and you perturb the entries a little bit, it can change the spectrum very drastically. Now, there are many different kinds of examples of this, but maybe the canonical example is just a Jordan block. So here, consider this matrix A. It's an n by n matrix. It's just a Jordan block. So 0 is on the diagonal, 1 is on the super diagonal. All of its eigenvalues are equal to 0 because it's upper triangular. You can see that. But if I add a tiny perturbation to the corner of this matrix of size 2 to the minus n, so exponentially small perturbation, then it's easy to see that the eigenvalues become half times roots of unity. So they go from being 0 to being half, to being, so they move by a huge amount, 1/2, under this tiny perturbation of 2 to the minus n. And this is really the reason people have not been able to prove things about normal matrices, because the eigenvalues are highly sensitive, and we have to work in this floating point model of arithmetic where everything is noisy. So how can we? That's the challenge. So any questions about this? Yes.
Yeah. So if this is the case with non-normal matrices, then how do you justify using the backward error approach? Because
right. Yeah. So the backward. So that's part of the reason backward error is justified. So this, what I've shown you is the worst case, right? So the actual answer is you should not try to solve this problem in floating point arithmetic. You just cannot. It's impossible, right? So the right way to think about it is you should try to solve problems which are which are stable under perturbations. And that's why backward error is a good notion, right? Because you should try to solve problems with backward error epsilon. That's a meaningful activity if the answer doesn't change that much, if you change the input by epsilon.
Yes.
Right? And so that's so I'm actually not proposing that I'm going to give you algorithms that solve this problem, right? What I'm proposing is that actually these roots of unity, first of all, they are a good backward error solution to the eigenvalues of A, because they are the eigenvalues of a nearby matrix. What I'm trying to say is that this type of phenomenon, suppose you have an algorithm that does something, generates a sequence of matrices. This could happen at any point along your analysis of your algorithm. And the difficulty is it just makes it hard to prove anything about the analysis. That's all. Do you see what I'm saying?
So I guess you need to assume some form of stability on the solution if you
Well, so in the end, we're not, no, that's the point. So the backward error model, somehow that's built into the definition, right? That if you give me an unstable matrix, I'm allowed to find a nearby stable matrix if it exists, and then give you the output of that problem. So the beauty of what we're going to do is we're not going to assume anything, and we're still going to be able to prove results of this type precisely because of the backward error, the flexibility that backward error gives you. You're allowed to regularize the input a little bit.
Okay. Okay.
Yes. So, but that's a great question.
Okay. So thank you.
Yeah. Okay. So that's the formalization of the problem. Any more comments or questions on this? Okay. So let me now give you 4 different algorithms for solving this. So the first is the algorithm we all learn in, high school or whatever. And this algorithm, I guess, goes back to the 1800s. I'm not sure who came up with it. Maybe Cayley or Frobenius or I don't know, somebody like that. And the idea is very straightforward. The eigenvalues of a matrix are the roots of its characteristic polynomial. So we construct the characteristic polynomial determinant of zi minus a. That's a univariate polynomial. And now we find the roots. Okay, well, of course, we've just kicked the can to this other problem. How do you find the roots of a polynomial? Well, you can't do it exactly. You have to also do it approximately. And we basically appeal to this huge literature on this problem, going back hundreds of years, culminating in this theorem, initial version due to Schoenhager from 82 and the final version due to Pan from 2002, which says, if you give me a rational polynomial with roots in the unit disk, then I can find epsilon approximations of all of its roots using n squared log 1 or epsilon bit operations. Okay, so there exist algorithms for finding approximate roots of polynomials with this kind of complexity. Okay, so that sounds great, right? Then maybe here's my algorithm. Given a matrix, let's assume its norm is bounded by 1. The algorithm has 2 steps. Compute the characteristic polynomial using, whatever method, linear algebra method you want. And 2, then use this root finder to find approximations of the roots. That's the first algorithm many of us would think of to find eigenvalues. I haven't said anything about eigenvectors. This is just eigenvalues. So any questions about this algorithm? Okay, so let's think about how this algorithm actually does. So there are 2 observations I want to make. One is, if you actually do this on a computer, the coefficients of a characteristic polynomial in general are huge. So here's an example I worked out. I generated a random 100 by 100 matrix with eigenvalues with random entries equal to plus or minus 1. You can check using random matrix theory that you expect the eigenvalues to lie in the interval minus 20 to 20, so not too big. And I asked MATLAB to compute the characteristic polynomial, and it did. These are the coefficients of the characteristic polynomial. It took me several minutes to do this, like 4 minutes or something like that. And the main feature I want to highlight is the coefficients are huge, right? So there's a 100 by 100 matrix. These numbers, I don't know how many digits they have, but they have over 100 bits. Okay. So this action of computing the characteristic polynomial, while it sounds very nice mathematically, is extremely slow and generates these polynomials with huge coefficients if you actually try to do it. And in general, you can easily see that even for nice symmetric matrices, the coefficients blow up exponentially in the size of the matrix. That's observation 1. Observation 2 is a famous example of Wilkinson from 1965, which is that the roots of a polynomial are extremely sensitive to changes in the coefficients. So this is a famous example of Wilkinson. Here's a very vanilla kind of univariate polynomial w of z, which has roots at integers 1, 2 through 20. And they're all real and so on. There are these green circles in this picture. And now if you consider a tiny perturbation of this, you perturb one of the entries by 2 to the minus 30. Then you get these black dots as roots. So the roots completely, these black dots, I think, are if you apply a few different random perturbations of this size, that's what you get as the roots. So indeed, the eigenvalues are roots of characteristic polynomial, but this is an extremely sensitive representation of the eigenvalues. If you perturb, in general, if you apply exponentially small perturbations to the coefficients, this will totally blow up the roots. So as a result, even if you want to find this method, use this method to find eigenvalues of a Hermitian matrix, you need to store these huge coefficients very precisely. There's no way around this. And so you need to actually store the coefficients using n bits of precision, where n is the size of the matrix roughly. To store numbers of size 2 to the n, you need n bits of precision. And so the end result is that this algorithm is very slow. So you can do this, but you need to do everything with n bits of precision. And there's a theorem of Pan and Chen showing that indeed this is sufficient. So the total runtime using this approach is n to the omega times n plus n squared log 1 or epsilon bit operations. Now, as n to the omega is this is the exponent of matrix multiplication. Currently, its theoretical bound is 2.37 something, but really in practice, it's close to 3. So the fast matrix multiplication is not really something that's fast in practice. But really, the thing that kills you is this extra n. So because this is such a brittle representation of the eigenvalues, you need to use very high precision, and this doesn't really work for large matrices. So it does have some pros. One is it actually gives you forward error. Once you go through the trouble of of storing these things with such high precision, you actually get forward error approximation of the eigenvalues. So this is useful in applications where forward error is required, like if you're doing representation theory or something like that. But it's really too slow for most applications. Even 100 by 100 matrix, you cannot really find eigenvalues using this. So that's the first approach, which is quite classical. Any comments or questions on this? Okay, so I'm going to summarize the different algorithms in this table. So the first one is a characteristic polynomial method. The running time is roughly matrix multiplication time, but the bottleneck is you need this n bits of precision. So the way to think of this conceptually is that this algorithm uses very high precision. It does get you high accuracy in the sense that you can make epsilon very small, and because it's under the log, the running time will not blow up. So that's algorithm 1. And for many years, there was this open question, which is there any provable algorithm that uses the type of precision that we know we can get in the Hermitian case? Is there any algorithm at all that can provably solve this backward error eigenvalue problem using log n over epsilon precision? This was explicitly asked by Demel in his textbook in 1997. So this question was open until 2015. And I'll now present the next algorithm, which solves this question, which makes progress on this question. And this is based on a method called homotopy continuation, which is essentially geometric in nature. A completely different method. Okay, so what's the idea of homotopy continuation? So this goes back to Lahai in 1934, but really this was popularized by Smale in the 1980s. So here's the idea. So you want to find the eigenvalues and eigenvectors of A, right? Okay. So the idea is you start with some other matrix, A naught, whose eigenvalues and eigenvectors you know. Let's say a diagonal matrix. So it's trivial, right? You know the eigenvalues and you know the eigenvectors. And now let's call that A naught. And then you slowly deform A naught into A via a homotopy. So this could be any continuous homotopy, but let's look at a linear homotopy, which is just A sub t is just the average of A naught and A1 with weight equal to t. So A sub naught is A naught and A sub 1 is equal to 1. And if you slowly increase t, then you're slowly deforming A naught into A1. And the idea, the high level idea, is that if you move very slowly, you should be able to keep track of the solution. The solution should also change slowly. And maybe there's some way of, updating the solution as you move along this homotopy. That's the high level idea. Now, to be more mathematically precise, here's the setup. So you define a variety, which is the set of all triples A, D, and V, so that A is equal to V d V inverse, and V has unit norm columns, and D is diagonal. Okay, so that's a subset of C n cross n cubed. It's a triples of n by n matrices. And the points on this variety, so it's a variety, it's a set of solutions to some polynomial equation. The set of points on this variety, these are matrices along with their diagonalizations, right? So this contains all possible instances of this diagonalization problem. So let's call that M. And now inside here, there's a particular set which is a little bit problematic. Let's call that B. That's the set of that corresponds to a set of matrices with 2 eigenvalues. Sorry, with a double eigenvalue. Okay. Now, the reason this is the reason this is I'm calling this ill-posed is that if you have a matrix with a multiple eigenvalue, the eigenvectors are not unique. And the function which maps the matrix to its eigenvectors and eigenvalues, that's not differentiable. You can check it's continuous, but it's not differentiable. So that's why these are ill-posed. Arbitrarily small perturbations of the matrix, if you're in B, can lead to arbitrarily large changes in the eigenvalues and eigenvectors. So let's call that B. In this cartoon here, I have this manifold or this solution variety M. And inside here, I have this other variety B, which is a set of ill-posed instances. And easy to verify fact is that if you look at this map from T, which is the homotopy parameter, to the matrix A sub T, D sub T, V sub T, then that's a smooth map on the complement of this ill-posed set. So that's just a highbrow way of saying, if you deform this and you never encounter double eigenvalues, then the eigenvalues and eigenvectors are differentiable functions, and that's all. So this is, okay, this now suggests what you should do. You should find a path which avoids this B and which is smooth, and which is smooth in some quantitative sense, and then maybe you can discretize it somehow. So this is the challenge. Find a path avoiding this ill-posed set B and a way to efficiently compute points on it. So any questions about this high-level idea before I get into the more specifics?
This homotopy is still the straight line homotopy, or
so the homotopy, okay, so the homotopy is defined in the space of A only, right? The space of matrices, that's a straight line homotopy. But if you now plot what the image of this homotopy looks like in this solution variety, which is now in the triples of matrices, it will be curved in general. Right? So if you look at the so the homotopy is still straight line, but if you look at the curve in this manifold, where you also look at the eigenvalues and eigenvectors, that will be curved. Yeah. Any other question? Okay, so how do we turn this into an algorithm? So the key ingredient, which was due to Smale and refined by Renegar in the 1980s, is the following lemma, which says, in a much more general context, but in this context, it says, if you have a point on the solution variety whose distance from this ill-posed variety is lower bounded by square root h, okay, by some parameter, so it's quantitatively far away, then you can move along this homotopy using a time step of size h. Okay, so the farther you are, the bigger step you can take. And specifically, what you can do is given, A sub t, D sub t, V sub t, if you're square root h away from this bad variety, then you can find A sub t plus h. You can evolve time by h using Newton's method. Okay, I won't say what that is. It's some standard optimization thing that was discovered by Newton. Maybe many of you know about it. It's some kind of local optimization procedure. But anyway, there's an efficient way to move along this homotopy as long as you're far away. So this is a quite influential lemma that was then used to solve all kinds of other problems. And now the challenge.
Can I ask the question?
Yes.
Yeah. So first, the Newton is Newton-Raphson, is it?
Yes.
Okay. And the second is, so I probably missed this, but you said that first of all, A0 probably is a matrix which avoids B, obviously.
Yeah. So yeah, you're toast if A0 isn't B.
But you're also assuming that A1 avoids B, that the matrix A itself avoids B, because otherwise you can get only so far until the A1.
Exactly, precisely. So what this lemma says is you need to find an entire path which avoids B.
So you keep going smaller and smaller.
Yeah. Well, I mean, if the whole path is well separated from B, then you can take large steps.
Yes. But otherwise,
and this is the challenge. How do you find? So the issue is you don't actually know what these eigenvalues are, right?
Right.
So you have to somehow find this path without knowing what the eigenvalues are.
Oh, wow. Okay. Yeah, that's a good point. Yes. Oh, wow. Yes. Okay. Thanks.
Yeah. The only thing you know is the A's. You don't know the D's and the V's. If you knew those, or you know them slowly, but you don't know the whole path. Yeah.
Oh, okay. Yeah. Thank you.
Now, the beauty of this is this reduces the algorithmic question to a purely geometric question. It's a question of finding a path which is well separated from some variety. This is a geometric question.
Right. So, by the way, even if you do keep getting successful, eventually, and if like if you somehow knew that your matrix A does have some repeated eigenvalues, then eventually, I assume you would have picked smaller and smaller H's.
Absolutely, yeah. So if I give you again, if I give you an A which is inside the bad variety,
right,
you're toast, right? You're never going to be able to get there using this lemma.
In finite steps.
In finite steps, yeah. In infinite steps you could, but you will not have an algorithm. So indeed, that's a great observation. The input matrix you give me better not be inside B, right?
Right. But that you can probably check by the characteristic polynomial and its derivative or something, right? To avoid multiple roots. I mean, in general.
Yeah, well, that's extremely slow, though.
Computing it is bad. Yeah, computing it is.
Yeah, that's extremely slow. And we want something that always works, remember?
Right, right.
So
yeah,
we don't want to do that. Yeah. Okay. So this is the challenge. Now, this challenge was solved in 2015 by Armentano, Beltran, Bergesser, Cooker, and Schubb. And their key technical contribution is the following lemma, which is sort of a result in geometric random matrix theory. Here's what it says. If you give me any A0 and A1, and you look at a random Gaussian matrix G. So that's a random matrix whose entries are IID complex Gaussians. And now you perturb A1 by epsilon times this Gaussian. So you slightly perturb one of the endpoints. Okay. So now you have a random path in some sense, right? Because you perturbed the endpoint. Then the claim is that path is well separated from this bad set with high probability, and the separation is a epsilon over n squared. So epsilon is the size of the random perturbation, right? If you don't do random perturbation, you can't prove anything. But the bigger the random perturbation, the more separated you are with high probability from this bad set. Okay, so this is their key result. It says, oh, don't, instead of trying to do something smart to find this homotopy to avoid B, just add some small amount of random noise. Now, why can we add this random noise? Well, it's because of the backward error formulation of the problem, right? We don't care if we're computing eigenvalues of A or of some tiny random perturbation. But importantly, we don't need to assume anything about A in this. This is true for every A1. Even if you give me this Jordan block or some horrific matrix, a small random perturbation will produce a homotopy path which is far away from B. Proof ingredients in this are some Gaussian integration on manifolds and something called the coarea formula. It's very geometric, uses things like change of variables formulas for Gaussian integrals on manifolds. But once you have this, you have an algorithm. Here's the algorithm. So given the input A1, first choose some diagonal matrix A0, which is not inside B. Just choose, that's easy. Just choose a diagonal matrix with distinct entries. Now produce a random Gaussian perturbation and perturb A by this epsilon times a random Gaussian. And now you have this random homotopy, A sub t. And now by this theorem, that's well separated from B by this epsilon over n squared. And so by the lemma, you can take step size that's epsilon squared over n to the fourth. Okay, and now you repeat this 1 over step size number of times. Yes.
Sorry, I was just saying, I'm still in sort of almost blown away that the lower bound there is so explicit in terms of epsilon and n.
Yes, it's amazing. It's amazing. I mean, sorry. Okay, there are some constants there. I'm dropping some constants, but the constants are not bad. It's one of these like very integrable type things, right? They use these very delicate algebraic formulas to compute everything, and in the end, I think it might even not have a constant.
Oh, okay. Yeah. So there are some universal constants there. Okay, but they are
no. So I'm not okay. I prepared the slides just ignoring universal constants in places like this, but actually, I think there may not be any constant, or it might be something like half or something.
Okay, yeah, even okay. That would still be amazing. Okay, but
yeah. No. So this is some very delicate, like integrable probability type of proof.
Okay.
Yeah, where you get some exact, like, nice bound. Okay.
Right.
Which is sharp when the matrix is 0 or something like that. So yeah.
Okay.
Yeah. So anyway, once you get this, then yeah, this random homotopy is good. You can take step sizes size epsilon squared over n to the fourth, and if you repeat this, you will eventually get your eigenvalues. So that's the algorithm. So to give you a sense of what this looks like, let me show you a MATLAB demo. So now I'm going to use this algorithm to find the eigenvalues of that same matrix, which of the same matrix which I had in the first example.
The one with those very large entries?
The one with the huge characteristic polynomial.
Okay.
So this is the initial matrix. This is the grid of eigenvalues. And now you evolve over time. I'm just showing you what's happening to the eigenvalues. So basically, you're deforming the matrix. And of course, the eigenvalues are going to change. And using Newton's method, you can compute the updates. And you get these kind of very cool looking pictures, actually. So these eigenvalues move around. Sometimes they come kind of close, but then they bounce off. They don't touch. They bounce off each other. It's actually the dynamics of this is still not properly understood. But anyway, so you keep doing this. And at t equals 1, well, you get the eigenvalues of your matrix.
An M minus B, isn't it?
Excuse me?
All this is in M minus B, right? The set M minus B.
Yeah, well, okay. So this is a picture of the eigenvalues of the current iterate.
Right.
So I'm not showing you the manifold because I don't know how to show you the manifold. But B, remember, B means that two eigenvalues collide. And the way you can see that here is that the eigenvalues never collided. In fact, they stayed kind of separated away from each other. That's the content of the theorem. Okay, does that make sense? Okay, any questions about this animation? Or I mean, this is not an animation, it's simulation, it's a real thing. Okay, so that's the algorithm. So now, okay, I somehow ended up at the beginning of my slides again. Oh no, sorry, here, yeah. Can you see the slide again? Yeah. Okay, so that's their theorem. And now when the dust settles, you get an algorithm which solves this with backward or epsilon for any matrix using n to the 10 over epsilon squared arithmetic operations with log n over epsilon bits of precision. Okay, now what's good about this? The log n over epsilon bits of precision, that's great, right? So this is a very analytic sort of geometric procedure. It's very stable against this floating point error. The nice thing about this is the bits of precision. It's very low, much lower than n. So it's the first provable algorithm for general matrices that uses logarithmic precision. In fact, it's the only one, even now. Now the cons you can kind of see. The dependence on the accuracy is polynomial. It's not logarithmic. That's actually very bad for applications because accuracy is usually something very small. And further, it's n to the 10. So this is not really an algorithm, that has a good worst case running time bound. So any questions or comments on this algorithm?
Just a quick question. Do you have to choose a different Gaussian for each iteration, or does it not make a difference, or how much difference?
No. You just choose one Gaussian.
One.
The whole homotopy is defined in terms of one Gaussian.
Oh, great.
So you just perturb the ending matrix, and then the claim is uniformly over this homotopy, you're bounded away from B.
Yeah. Oh, that's right. That's right. Okay.
Yeah. So one remark I want to make. So this seems to be a very slow algorithm, like incredibly slow. Now, the reason for that is really this algorithm. This is really a very general algorithm that can be used to solve all kinds of other things, like systems of polynomial equations. And we're just applying it to this matrix eigenvalue problem. It's really not exploiting the structure of the eigenvalue problem enough. That's kind of why it's so slow. We don't expect such general algorithms to be, well, I don't, for example, we don't expect them to be logarithmic in the precision. So that's algorithm number 2. Yes?
What about the eigenvectors in this case?
Yes. So as you're doing this, remember, in this homotopy, you're maintaining A, D, and V. V is the eigenvector matrix. So I didn't show you the animation of that. But yeah, as time goes by, the eigenvectors are also deforming and you're maintaining them. So in the end, you get the eigenvectors out of this. Does that answer the question? Okay, so again, yeah, the key point is because of the backward error, you can add a random perturbation, and then without assuming anything about A, you can get this conclusion. Okay, so then let's put this in the table. So the runtime here is much worse, n to the 10 over epsilon squared, but the precision is much better. So this, I would call this a low precision algorithm, which is good, but a very low accuracy algorithm as well, and it's also very slow. So this question, we can refine it. This is now, is there an efficient high accuracy algorithm that uses log n over epsilon precision? Okay, so this was the state of affairs for a few years. And the next algorithm I'm going to present improves on this. And this is a result from 2019. So this is an algorithm based on, I would say, approximation theory, function theory, complex analysis type ideas. It's called spectral bisection. So the algorithm itself is not really that new. It goes to it's based on ideas going back to the 70s. So the key player in this algorithm is something called the sign function of a matrix. So suppose I have a complex number z, which is not on the imaginary axis. I can define the sign function of that number to be the sign of the real part of that number. Okay, so just +1 for real part positive, -1 for real part negative, undefined on the imaginary axis. And now I can define the same thing for a matrix. For diagonalizable matrix, I can define the sign function of the matrix to be the matrix which has the same eigenvectors, but all the eigenvalues in the right half plane get mapped to +1, and all the eigenvalues in the left half plane get mapped to -1. So this, like this picture shown here. So what it does to the spectrum is very straightforward, but importantly, it preserves the eigenvectors. Now, why is this relevant? Well, the upshot is if you can compute the sign function of a matrix, then by looking at identity plus sign divided by 2, what that does is that just zeroes out the eigenvalues in the left half plane. So if you can compute the sign function, you can compute the spectral projector onto eigenspaces in the right half plane, or more generally, if you shift the matrix by some scalar t, you can compute the spectral projector onto any half plane in the complex way. So this is useful. I won't get into the details roughly. So Beavers and Denman realized that if the matrix has well-spaced eigenvalues, you can use, if you can compute the sign function, you can do divide and conquer. You take the matrix, you compute the sign function, you maybe shift it a little bit to get about half the eigenvalues on both sides of the imaginary axis. You compute the sign function, it gets you the projector onto the right half plane. And then when you multiply the matrix by the projector, you now have a problem with half as many eigenvalues. So then you do divide and conquer. I don't want to get into the details of this, but basically there's a well-known reduction saying if you can compute the sign function, you can diagonalize the matrix. In fact, and this reduction works in matrix multiplication time. It's extremely efficient. So then the question is, well, how do you compute the sign function? So the rest of the section, I'm just going to talk about computing the sign function. Any questions about the sign function or?
Sorry, so you want to compute the sign, so you want to compute sign of A basically.
Yeah, sign of a matrix, yeah.
Without knowing sign of B.
Yeah, you're given an A. And of course, this is only defined if the eigenvalues are not on the imaginary axis, right?
Sure, sure.
So let's assume, I mean, as you can imagine, we'll guarantee that by a random perturbation, but
Yeah, exactly.
Then you want to compute sign of A.
Yeah, so I'm given A with the knowledge that, yeah, whatever. You know, the sign of D is, the eigenvalues avoid the imaginary axis, the perturbation set by some real scalar. But yeah, and then I don't know what they are, just that they avoid this axis, and I want to compute sign of A.
Yeah, which is a matrix.
That's the, okay, great. Okay, thanks.
Okay, so this was answered for numbers probably in the 1800s, but a reference I found is due to Roberts in 1972. This was studied by Zolotarev in 1877, who probably knew this, but here's a way to compute the sign function of a number. So you define this meromorphic function, z plus z inverse divided by 2. So notice that this has 2 fixed points, +1 and -1. Those are the only 2 fixed points. Okay, fine. So now the idea is, well, maybe if you just keep applying this function to this number z, it will converge to one of the fixed points. And indeed, this is the case. And to understand this convergence, you need certain sets in the complex plane called circles of Apollonius. So let me define these sets. So alpha, let's say alpha is a number strictly less than 1, a positive number. I'm going to define C alpha plus to be the set of points in the complex plane, which are whose ratio of the distance to 1 over the distance to -1 is at most alpha. So this is a maybe thousands of years old fact that such a set is a circle called a circle of Apollonius. And similarly, we define C alpha minus the set where the distance to -1 is at most alpha times the distance to +1. And this gives you a family of circles in the complex plane, which are not centered at +1 and -1, but contain them. So C alpha plus are in the right half plane, C alpha minus are in the left half plane. Now, the key fact about this function is that it maps C alpha plus or minus to C alpha squared plus or minus. Okay. So this is saying this contracts these circles in a very specific way. So remember, if alpha is equal to 1, then the C alpha is just the entire right half plane. If alpha is equal to 0, the set is just +1 or -1. What this key fact is saying is when you apply G, it squares this circle parameter alpha. So it shrinks it. But now you have a clear algorithm, right? To compute the sine function of a number, you take the number, you apply G, and you just keep doing it. So if your initial Z is in some circle parameter alpha naught, then after k iterations, you will be in some circle of parameter alpha naught to the 2 to the k. So this is amazingly fast convergence. And then you can see that this, if you run this for k steps, if you run this for roughly log of 1 over 1 minus alpha naught, so this measures how far your initial point is from the imaginary axis, plus log 1 over epsilon steps, you get an epsilon approximation of the sine function of a number. Any questions about this? This is like elementary. It's not even complex analysis. It's just, I mean, yeah, it's some very basic fact. Okay, now this is how to compute sine function of a number. Now the beauty of this is, how do you compute the sine function of a matrix? Well, it's the same thing. So by the spectral mapping theorem, if you have any function g that's analytic in a neighborhood of the spectrum of A, the spectrum of g of A is g of the spectrum of A. So in particular, if your matrix has no eigenvalue at 0, actually, then this applies to this function g of A. So now you get an iteration on matrices. You just take a matrix and average it with its inverse. You keep repeating this. And by the spectral mapping theorem, the spectrum of your iterates will converge in exactly the same manner. Will converge to +1 and -1. And so as a result, if you run this for this many iterations, this should be A sub k. A sub k the spectral radius of A sub k minus sine of A will approach 0. So this is a specific notional approximation, spectral radius, not norm. But basically, the algorithm just works as stated for matrices. And so this is algorithm S. It's extremely simple. You start with your matrix, and you just keep applying, you just keep averaging with the inverse. And you do this log 1 over epsilon times, plus this log of 1 over 1 minus alpha naught prime, which is important. Then you will get an approximation of the sine function. So any questions about this algorithm for matrices for computing the sine function?
So how efficiently can you compute A inverse? Right? So because, or is there a simpler way to compute A plus A inverse?
No, you have to compute the inverse. So this downside of this algorithm is each iteration involves computing the inverse, which is expensive. It takes n to the omega time or n cube time or whatever. The nice thing is the number of iterations is tiny. It's log 1 over epsilon plus log of 1. I mean, this log of 1 minus 1 over alpha is very important, and we'll come to it later. But the number of iterations is small. So let me show you an example of what this algorithm looks like. Let me show you a MATLAB demo. Okay. So same matrix again. I'm going to run spectral bisection for 15 iterations. Oh, I see. Sorry, the figure got closed. Sorry. Okay, let me do it again. Yeah, so you start with this, and now you keep doing this, and you have these eigenvalues moving around in some way that looks kind of complicated, but really they're just moving around inside these circles, and then they converge to these point +1 and -1 in like 7 iterations. Okay, so that's the spectral bisection algorithm. Okay, now sorry, where's my slide? Here. Okay, so what's the problem? Anybody see what the problem is? Well, there are two problems. One is, how do you guarantee that these 1 minus alpha naught are not 0? So you're going to keep doing this, right? How do you guarantee your eigenvalues stay away from these lines? And maybe even more serious issue is, in real life, you don't get to do this exactly, right? You do in floating point, you add a little bit of noise at every step. And then this spectral mapping completely fails, right? Because you get matrices that don't even commute. And so this proof just completely breaks down in finite arithmetic. So these are the two issues. How do you avoid the lines? But more seriously, how do you say anything about this in finite arithmetic? You're doing something that's pretty heavy-handed, right? You're repeatedly inverting the matrix and adding noise. So how do you analyze this? And this was studied for maybe since the 80s. And there were some partial results which basically proved that if it converges, then it works. But there was not, no one could say how to prove convergence. Okay, so the recent result, which is in 2019, joined with my co-authors, is that if you take any matrix and add a small Gaussian random perturbation, then you can prove that this works. Both of these problems go away. You can prove that you always avoid the lines, and more importantly, you can, through a completely quite different proof, prove that this converges rapidly in finite arithmetic, in floating point arithmetic. So I won't tell you the details of this, but when the dust settles, what you get is you get a running time of matrix multiplication times log squared n over epsilon. So very good running time. Just log squared n over epsilon matrix multiplications. But precision is log to the 5 n over delta. Okay, so the running time is great. I mean, you can't really hope to do better than matrix multiplication times, and log squared in the running time is okay. But log to the 5 in the precision, that's not really practical, right? In real life, we have 64-bit computers. Log to the 5, if you're a computer scientist, you might think it's nothing, but you know, it's a lot. So this leaves us here, that we now have an algorithm with excellent runtime, high precision, but high accuracy, but low-ish precision. Log to the 5 n over epsilon, not log to the 1. And again, the random perturbation played a key role. So that's the third algorithm. Now, how much time do I have? I started a little bit late. Do I have like maybe 3 or 4 minutes?
Yeah, you can take up to 10 minutes. Not a
10
problem.
minutes. Okay, great. Perfect. In that case, let me pause and see if anybody has any questions. So this algorithm, I should emphasize, is not a new algorithm. It's a 1974 algorithm. What's new is this random perturbation and the proof. And I can say a bit about the ingredients of the proof. The key is that the proof I showed you studies the eigenvalues. The key is to study this thing called the pseudo spectrum, which is, okay, I won't say what it is. It's a set of all eigenvalues of all nearby matrices, and prove a pseudo spectral mapping theorem for this function g of z that we used. And then you need some random matrix theory, some least singular value estimates to prove that everything works out. So again, we have to analyze a random matrix, but we do it using different tools from random matrix theory from the Homotopy paper. Although recently we realized that you can actually use their result about distance from the bad set B to prove the random matrix theory results we need for this also. So there is a formal connection there. These are really just different ways of saying you avoid this set of ill-posed matrices. So any questions or comments on this? Okay, so that's method number 3, spectral bisection. That brings me to method number 4, which is a shifted QR algorithm. Now, the shifted QR algorithm is the oldest algorithm in this business, the oldest real algorithm. It was introduced by Francis and Kubanovskaya in 1961. And the first idea is to kind of change the problem a little. You don't try to compute the eigenvectors. You try to compute the Schur form instead. Okay, so every matrix is unitarily similar to an upper triangular matrix. So instead of trying to find the eigenvectors, you try to find this similarity. That's the first observation. And then the idea, which is not at all obvious, is the following. How do you find this Q? Well, you consider the following isospectral iteration. So you start with A not equal to your input matrix A. And now for at every iteration, you take your matrix AK and you compute its QR factorization. So you just do Gram-Schmidt or whatever, okay? That gives you a unitary matrix Q. And your next iteration, you just conjugate your current matrix with that Q. That's it. So this clearly doesn't change the eigenvalues, right? Because you're conjugating with unitary. Now, the amazing thing is you can show that if the eigenvalues have distinct magnitudes, magnitudes have distinct magnitudes, then this converges to an upper triangular matrix in the limit. And the rate of convergence depends on the ratio of magnitudes of the eigenvalues. This is not obvious, but it's not very difficult to prove. It's like half a page. It's very beautiful. But let me comment. So before I comment on this, any questions about this idea? So this was observed by Francis and Kubanovskaya independently during the Cold War. Now, okay, what is this business about this? Why are the magnitudes of the eigenvalues relevant? So let me show you an example to explain why. So if my matrix is unitary, then all the eigenvalues are on the circle, right? So all the magnitudes are 1. Now, what does this iteration do to a unitary matrix? Well, the QR factorization of a unitary matrix, the Q is just the matrix itself. So if you apply this to a unitary matrix, it doesn't do anything. So unitary matrices are fixed points of this dynamics. So that's why, I mean, that shows that if all the eigenvalues are the same magnitude, then something bad might happen, in particular if the matrix is unitary. So that's why this doesn't give you an algorithm. It doesn't work on unitary matrices, and if there's no bound on how slow it could be if you give me a matrix with very close by eigenvalues magnitude. So the second idea of Francis and Kubanovskaya, which is why it's called a shifted QR algorithm, is you can speed up the convergence by shifting the matrix. So you can change these unitaries. Instead of computing the QR decomposition of A, you can just shift A by some scalar times identity. And now the convergence depends on the ratio of the magnitudes of the shifted eigenvalues. And that can be different from the original magnitudes. For example, in this unitary case, remember, I had a unitary matrix, the magnitudes are all 1. This was a fixed point, it was bad. Well, if you shift the origin, then it's not a fixed point anymore. Right? If you shift the origin, the magnitudes of the eigenvalues become very different. Right? So this is a fixed point, but when you shift the origin, it's not a fixed point anymore. So this was the high-level idea. So the algorithm is now specified by shifting a function S sub k, which is a shifting strategy. And the challenge is, how do you choose the shifts? Right? You don't know the eigenvalues of the matrix. You're trying to compute the eigenvalues. If you knew the eigenvalues, it would be easy, but you don't know them. So you have to somehow find these shifts without computing the eigenvalues. So that's, before I tell you what some concrete results, that's a summary of the main idea in the shifted QR algorithm. Any questions? Okay, so what's known about this? Well, there's a famous result of Wilkinson and Decker and Traub from the late 60s. They found a strategy that always works for Hermitian matrices. This is a very subtle, beautiful thing. I won't tell you what it is. You can read about it in textbooks. So for Hermitian matrices, there is a function S sub k, which produces these shifts such that for any Hermitian matrix, this thing converges very rapidly. And it gives you an algorithm with this running time, n cubed plus n squared log n over epsilon, using log n over epsilon bits of precision. So this is the gold standard. This is the algorithm I cited in the beginning of the talk. Okay, and this is the algorithm that everybody uses. This is the algorithm used in MATLAB. This is the algorithm used in LAPACK. This is what you're using when you compute eigenvalues on a computer. That's a plus point. The downside is there's no, until very recently, nothing was known at all for matrices that are not Hermitian. So this was studied by people in dynamical systems in the 90s. And what they proved is that all of the known shifting strategies exhibit really chaotic behavior or slow convergence on if you throw away this Hermitian assumption. Definitely, if you go to non-normal matrices, you can have all kinds of weird dynamics that happen when you run this algorithm. Now, this picture is taken from a 1992 paper of Ryder. I won't carefully tell you what these pictures are. They're pictures of some basins of attraction for a certain shifting strategy that's used, that's called Rayleigh quotient iteration. And all I want you to see from this is that they're very complicated and it seems difficult to prove anything about them. So somehow that while this is great for Hermitian matrices, for non-Hermitian, the dynamic seems very complicated. And in fact, some interesting recent result was shown using some topological methods. It was even shown that if you have any strategy that always works, it has to be a discontinuous function. So somehow the space of shifting strategies was this mysterious thing. Okay, so the very recent result, which is in the process of being posted on the archive with Banks and Garza Vargas, is the following: that if for every matrix, if you take a small random perturbation, then we have a shifting strategy that converges rapidly. Okay, so there is a shifting strategy, which I won't describe to you, but you can go and read about it on the archive if you want. Such that if you take any matrix and add a tiny random perturbation, then it converges very fast with high probability. The running time is n cubed log squared n over epsilon, and the bits of precision is log squared n over epsilon. Now, I won't say too much about the proof. The basic idea is you shouldn't try to understand this dynamics on one step at a time. You should understand it on slightly longer time scales of about log n steps at a time. And this dampens some transient non-normality type effects. And then maybe even more, well, I don't know, another important ingredient is that we detect, like this QR algorithm, there are two obstructions. One is chaotic behavior due to non-normality. The other is getting stuck in some highly symmetric configuration, like a unitary matrix. And our strategy has some way of detecting, characterizing, and breaking symmetry, which always escapes these symmetric configurations. That's very high level, but that's roughly the thing. Anyway, so that completes this table. So now our algorithm does n cubed log squared n over epsilon. That's good enough. And precision log squared n over epsilon. Okay, so that's getting there, but that's not log n over epsilon. So that's it. So that's the talk. The common theme is we use randomness to analyze all three algorithms. And maybe this explains why this wasn't done 50 years ago, because people weren't thinking about randomness. And this question is still open. Is there an efficient high accuracy algorithm that gets logged to the 1 epsilon, n over epsilon? We don't know. So that's it. Any more questions?
I have a question.
Mm-hmm.
Hello. Yeah, so
yeah.
yes, all of the improvements that you've stated in this talk. So you're changing the matrix first, and then you're trying to diagonalize, right?
That's right.
So can you translate this to some form of forward error? Like this again goes back to what I was saying.
Right. So so if the matrix has multiple eigenvalues, then it's impossible to get forward error for the eigenvectors, just because even an infinitesimal perturbation can arbitrarily change the eigenvectors. For eigenvalues, yes, you can turn this into results about forward error. I mean, yeah. So roughly speaking, you can define a certain condition number for the eigenvalues. And if you run this algorithm with parameter epsilon divided by that condition number, then you'll get an epsilon forward error solution. And I mean, okay, similarly, yeah, I mean, you can prove things like if your matrix is distance h away from this bad set, then if you run the algorithm with, if you run the backward error algorithm with accuracy h times epsilon, then you'll get an epsilon forward error solution. You can prove things like that. And those things could be useful because remember, this epsilon is going inside the law. But if you strictly want forward error for matrices with multiple eigenvalues, you cannot do it in floating point. It's just impossible.
Okay.
And this other line of questions is still open, that in a different model of computation where you do exact arithmetic with rational numbers, what's the complexity of computing eigenvalues and eigenvectors and forward error? That's still open. The best bound we have is, I think, n to the omega plus 2, and we don't know if you can beat that.
Thank you.
Yep.
If there are questions from the online audience, please unmute and ask. If there are any more questions, let's thank the Srivastava.